вести заседание, и я хотел бы объявить о начале доклада профессора Дэна Молдована. Это не тот Молдован, которого многие из вас знают. I will say a few words in English about Professor Dan Moldovan, so that you would know that I'm saying all the good things about it. He's a professor in the computer science department at the University of Texas at Dallas, and the co-director of the Human Language Technology Research Institute. And his research is focusing on natural language processing, semantic technologies, machine learning, artificial intelligence, parallel and distributed processing, and other language-related technologies. And Professor Moldovan is now working on several major projects, including extended WordNet, computational lexical semantics, ontologies and semantic technologies, knowledge acquisition from text, and distributed natural language processing. Please.
Thank you very much. Good afternoon, everybody. Wait until the end. I'll make sure you're followed at the end. It's good to be here, and it's my first time in Russia. I really enjoyed it. Very interesting experience. So I want to share with you some work that I've been doing over the years to represent text. This is what my focus of my work is: how to transform text into some knowledge that can be used by the machine to build applications. So I'm going to say something about explicit, implicit, and implicated textual information. And this is something that very few people talk about. A lot of work has been done in pragmatics about implicatures, but I'm trying to bring that work into the context of representing textual knowledge. So while the work is in NLP and has some certainly computational linguistics roots, the work also has an engineering dimension of the system. So related to that, this work has been implemented in a company called Limba, and what I'm about to tell you today actually has been implemented in prototype. I don't have time to show the demos, but I have some snapshots. So here's an outline of the talk. I want to introduce the explicit, implicit, and implicated text meaning. Hierarchical organization of text. This is a way that I think is superior to organize the knowledge you extract from text, and then a model for representing this knowledge, and reasoning for these forms of knowledge. And at the end, conclude some challenges that I see. So, to put this work in perspective, at one end of the spectrum, the simplest part is to look at the text and the word meanings and just figure out what the text is telling us, without any form of inferencing or try to extract any more information from text. Just look at the text and try to understand the meaning of the words and collectively the meaning of text. So if you look at this sentence, the car is cheap. This sentence tells us that the particular automobile is inexpensive. That's all you can conclude. But then, if you want to draw some inferences, you are going to extract some implicit information from text. So this is the middle layer here. And with the help of some inference rules, we can extract more information from a sentence in addition to what the sentence is just telling us at the surface pattern. So, for example, if I look at that sentence, the car is cheap compared to some, it's inexpensive compared to some other automobiles. But here's a more interesting sentence that I came up with one of these evenings. The king of Spain hunts elephants, And this is true. Juan Carlos was caught in Africa some months ago, 2 months ago, so hunting elephants. So what you can derive from here is that the King of Spain is a hunter, and he hunts elephants. Probably he broke some laws, because hunting elephants is not really a sport that is like any other sport. So there are the fact that Spain has a king, right? There are some implied information that is hidden into the sentence that could be extracted with some inference rules, presuppositions, and others. And yet, at the other end of the spectrum, there is implicated information, and this is the kind of information that has almost nothing to do, well, very little to do with the sentence that has been uttered. It has to do with the context in which that sentence has been uttered. So this is unlike the previous two forms, where we didn't care about the context. In here, in implicatures, we have to know the context, and the context will make different inferences. So, for example, if I say that car is cheap, then this can be a derogatory remark about the person driving a car, that that person cannot afford to buy a more expensive car. And in some countries, that's a status, the kind of car you drive, the status who you are, unfortunately. Or it could be just the opposite, that the driver, the owner of that car, is a very wealthy person, and he didn't want to show off, and his car is not cheap compared to other cars, but it's cheap compared to what he could afford. So it tells you something about the person. It depends on the context. So looking at the sentence from multiple contexts, you can draw different implicatures. So to continue this, we just completed a 1-year project where the task was to derive implicatures from Twitter conversations, because that's where the implicatures really occur in conversation, because you have a context in conversation. So here's a snippet of a conversation. Dinner's ready, prawns, grouper in some sauce, vegetables, rice, and sharks, thin melon soup, still waiting for lotus root soup this week, saying A. B saying, yee, lotus root. And A says, so what you are having for dinner? Now, there is a lot that is implied here in this exchange, right? And the job would be to build a system that could extract those implicatures from the sentences. So if you look at these sentences only from explicit point of view, then we figure out that there is a dinner, we understand the meaning of dinner, and it's ready, and the fact that all these food are part of a dinner, and so on. If you apply some inferences to these sentences, then you might get that this expression means some disgust, feeling, and also, you know, that sauce is part of a dish, and soup is a dish, and dinner is dish is part of a dinner, and so on. So with some inferences, I can draw even more information that I have was able to extract from explicit conversation. But yet, if you look more carefully, you see that A is very excited. There is this exclamation there, and we talk about gourmet dinner. So A is very excited for cooking that dinner, and B does not agree. It says E, lotus soup, lotus root soup. So it does not share the enthusiasm that A had about his gourmet dinner. And then A is saying in return, so what are you having for dinner? Like it's kind of getting back to B. So if you don't like my dinner, what do you have for dinner, right? So there are some feelings that are being exchanged here that we'll be able to capture only if we consider the implicators. Okay. So now if I look at the whole thing, the whole picture, at the left-hand side, I see the meaning of text, just the the words and the corrected meaning of words. And I'm not going to imply here that this problem is text understanding solved by any means. There's still a lot of work to do, but still that does not prevent us from looking at some more complicated aspects of extract knowledge from text. So the very simple aspect is just the meaning of text. In the middle, you have some inferences that can be drawn using some semantics. Yet, at the other end of the spectrum, you have the implicated knowledge that uses not only semantics, but pragmatics and context. Right? So the context is not necessary for explicit and implicit meaning. And the topic of this conference is certainly extracting the sentiments and opinions from text. And I thought I'll put here my view at the left-hand side part of the spectrum. You have some sentiments and feelings that could be extracted, but there is an even richer source of sentiments and opinions if you try to get what is implicated by the context. All right, so now that we put this three aspect of text processing into perspective, let's look at some more examples of implicatures, and then I'll get back to how to organize the knowledge hierarchy. Let's look at this exchange. Are you inviting Mike to the party? A is saying, no, I'm inviting nice people. So, from here, we can conclude that Mike is not a nice person in his opinion. The opinion of Mike is that he's not a nice person. But that's only one interpretation. Could be another interpretation in which A knows that has been some exchange between B and Mike, and maybe it was B's fault, and A said, aha, you are revengeful. You are not inviting him because you had an argument with him, right? So that is a context that's being projected, and that changes the meaning of the inference. When we see this sign here, A, that means an implicature. It's not an inference, but it's an implicature. Couple more examples. Do you want to play tennis this weekend? Says John to Mary. And Mary says, I have to study. Now, maybe scenario one, maybe Mary is sincere. She's ambitious or underachieving student, and she has to study. Or Mary just wants to put John off, say, well, I don't want to go out with you. But does not say that. And says, we're refusing John politely. I have to study. And we see that all the time. Paul is saying, has Bob got a girlfriend? And George says, he's been playing a lot of tennis lately. That could mean, no, he doesn't have a girlfriend, he has a lot of time, he's just playing tennis instead. Or, yeah, he has a girlfriend, spending time with her playing tennis. And this can be reinforced by Paul saying, he always liked athletic girls, right? Which makes us believe for sure that he has a girlfriend. Right, so that's the implication. And that is something stated here in George's response or Paul's follow-up. The fact that he has, we don't have an answer yet, but we can infer. So the problem that I wanted to address in that project that just finished was, can I compute the implicatures? So the conclusion is yes, you can compute the implicatures, and there is a nice theory put out by Grice in late 50s, early 60s, and then he continued to 70s about cooperating principle. And this theory can be transformed into some logic, and then you can put that logic to work to draw some implicatures. So the cooperative principle enunciated by Grice was that contribute what is required by the accepted purpose of conversation. And there are some maxims that Grice has stated. Is the quality maxim, say only what you believe to be true and only what you have evidence for. Quantity maxim, be as informative as required, no more, no less. Relation maxims, be relevant to the topic at hand. Manner maxim, be perspicuous, avoid obscurity, ambiguity, be brief, report. So these four maxims have been criticized by some, but many people agree with the maxims, and we tested the maxims, not only in English. These maxims are true across languages, by the way. And it's kind of a principle for cooperating activities, because if you work with somebody and if you say, give me the hammer, try to build something, then you're not going to give that person a wrench or something else. You're going to give them the hammer. If you don't give the hammer, you're not cooperating, right? So respecting these maxims is certainly important for doing either talking together or doing some work together. How are the implicatures computed? Well, they can be computed in three ways. Either we observe the Grice's maxims, and or we violate one maxim at the expense of the other, or we just flout the maxim. Now let's look at the three examples. This happened to me. I was in a building where the company is, and there was a doctor's office near the corner, and I saw this woman with a baby in her arm, and she asked me, do you work here? And I said, the doctor's office is around the corner, because I knew exactly what she wanted. I didn't say, yes, I work here. That would have been violating the maxim. So my answer was to the point, trying to help her, and the conversation has respected all the maxims. Right? Or you can violate one maxim, like where's Limba located? And B says somewhere in Dallas. Well, B violates the quantity maxim, says somewhere is not precise, but cannot be more specific because it will violate the other maxim that is even more important, that will lie, will say something that's not truthful. So really the implicature here is that B does not know where Limba is, but still gives some information that is helpful a little bit, not completely. Or you can just violate the maxims intentionally, right? And you can say, are you playing tennis this weekend? A lot of my examples are about tennis because I like tennis. People can play tennis here because the rain. And B saying, so are you playing tennis this weekend? You know I don't like tennis. And it's just the opposite is true, because B is an avid tennis player, and he just meant to say, yes, of course, right? But it's just saying, you know I don't like tennis. So he's violating intentionally the maxims. So inferences are derived that way. So how to calculate, how to extract these implicatures from conversations. So we have a speaker, S, and here, somebody who hears the conversation, H. And the logic is like this. The speaker S says P, whatever is saying, and there is no reason to think that S is not observing the maxims, or at least the cooperating principle. And in order for S to say P, he meant to say something Q related to P. So there is P that's being uttered, that's being said. But there is also Q that's not being said, that is certainly related to P. And S also knows that P, that this Q is a common knowledge. And the hearer knows this Q, will understand this Q. And S has done nothing to prevent the hearer from thinking Q. So therefore, S intends H to think that Q is true and saying that he has implicated Q. So in order, it would be boring for us to communicate in terms of expressing everything, right? Nobody cares that outside it's raining right now, unless we go outside. So we should not say things just for the sake of saying. We should say things that are relevant, that are informative to trying to help the conversation. So this is how this process can be implemented in some software to extract some implicatures. Here's a more specific example. A is saying, what on earth has happened to the roast beef? And B says, the dog is looking very happy. And A assumes that B is following the maximum of relevance. Right? B's remark will not be relevant unless the dog has something to do with the roasting, right? If B's utterance was something is raining outside, has really no direct connection with the beef. But we know that dogs like beef, right? And the fact that he's very happy means that has eaten the beef, because that will make the dog happy. So that's a common knowledge that has not been stated, but it's kind of related to, has been stated here. Dog is looking very happy. And that inference, implicated, the dog has eaten the beef, can be inferred by A, just from what B has said. All right, does that make sense so far? Okay. Yep. So now I'm changing gears a little bit, talking about coming back to the whole spectrum of knowledge from explicit to implicated, and see how we can organize that, and then how we can compute it. So this is my view, shared by some people. I'll say that if you extract knowledge from text, you ought to put some order into that knowledge that is being extracted from text. And we want to look at this knowledge in a hierarchical way. So you have text, you parse the text syntactically, and that will give us some lexical concepts that are extracted, like name entities, collocations, normalized temporal expressions, and you can even transform that text into some logic form via the syntactic parsing. So that's a very low level where a lot of details are extracted from text. If you go up in a hierarchy, then you want to extract semantic relations between concepts, right? And then you want to extract some context, maybe temporal or planning concept. If we say the train scheduled to leave at 10 o'clock, we do not know if that train has left at 10 o'clock or not. We only know that it's supposed to leave at 10 o'clock. So that's a context that if it's not stated otherwise, we believe it's true, but we do not have the information that the train has left at 10 o'clock. So that's the kind of information you want to import here in context. And then events, in my opinion, events dominate the text. The whole thing is about events and filling in some details about events. So if you're able to detect events in text, then you get to the most important information from that kind of text. And then you have event relations, like one event influences another event, causing or co-occurring, and so on. And then on top of that, you have macro events, because events can be composed into the macro events. For example, the dialogue would be a macro event, and my talk is just a small event. It's part of dialogue and part of this afternoon conversation and so on. So the advantage in organizing this knowledge hierarchically is that here, at the lower level, you have a lot of details. And as you go up in a hierarchy, you have fewer and fewer details, yet more important details. And it's easier to do reasoning at this higher level of knowledge because there are fewer things to worry about. And yet, if you need to fill in some details for reasoning, then you can go down, extract more. And there's this ladder here, up and down, and you can do the reasoning at higher level, but if you need details, you can go down and extract. So let's look at this example. Two sentences. Gilda Flores' kidnapping occurred on January the 13th, 1990, a week before he had fired the kidnappers. So the first sentence is represented here. There is a name, proper name, Gilda Flores, and then there is a kidnapping event that's represented by the circle here. Kidnapper is the theme of kidnapping, is the one that is kidnapped. It occurred on this time, January 13, 1990, it's a date. And the next sentence is that a week before, and you can calculate when the week before is, subtract 7 from 13 is the 6th, so we know the date, and then he had fired. There is another event here for firing. I'm not sure if you can see this, but I'm just leaving it. It's a little bit small. And then kidnappers is the theme of being fired. So we have here a lexical level representation of these two sentences, and at higher up we abstract these two sentences. There are about two events. One is about kidnapping of this person, and the other one is a firing, and there is a relation between the two, and one has caused the other. In other words, firing, laying off people was the motive for kidnapping, right? So this influences that event because it occurred before, and also there is a relation, the meta relation between these two events. The whole text is about revenge. If I had to summarize the whole sentence, it would be about revenge, right? Right? Okay, so now how do we put this into machine language, right? So at the lower level, we have a logic form that is being derived from the sentence, and here we are using a kind of Davidsonian logic with the fixed positions for the agent, the eventuality, and the objects. So here you have the tilde floris, it's a proper noun, it's also a human, it's detected by the mimetic recognizer, and there is the kidnapping, which is the event, and we have the time of that event, and the same thing for the other sentence, and the semantic relation that I extracted is the theme of this event is tilde floris, was being kidnapped. The agent is X4, and X is a dummy, and there is no agent. And well, actually, is what's being fired. So there is a correspondence between this X4 and X4 here, and there is a during relation, and then there is an occurrence of that event E1 and the occurrence of event E2, the firing, and then there is a cause relation and before temporal relation. So that is the logical representation of these two sentences, which can be understood by the machine. Now, in order to do these kind of things, you need a lot of tools, and that is really what prevents many groups and even institutions, companies, to be able to do the deep processing of text. You need to have a lot of modules. So you start with the tokenization, then part of speech tagging, sentence bound detection, name entity recognition. Many people have this, and concept tagging, syntactic parsing, so far so good. But then you get to wordsmith ambiguation, context detection, semantic parsing, which is much more difficult to achieve, coreference resolution, and this is coreference within a document, cross documents, for events and for other entities, quite difficult problem, and then event extraction, and then here's some semantic outputs. I'll say something about that. So you send in text here, and then at the end, you have to get structure organization of text, and this is what I want to achieve. But I'm in this business of extracting knowledge from text, so that's my output there. And then once I get this output in some format that's acceptable, then I can build all kinds of applications. About semantic relations, because this is one of the important boxes in that pipeline of modules. You have to decide what semantic relations you are interested in. Either you take a generic parser or build a dedicated parser for that particular domain, and you have to train the parser, the semantic parser, to extract some semantic relations. Now, if you're interested in our work on the semantic parser, there was a paper presented last week in Istanbul at LREC in some proceedings, and describes the details of that semantic parser. So there are some details here that I'm skipping, but if you are really interested, you can look at the paper. The main modules of the semantic parser has a bracketer, groups words together to figure out the arguments between which you want to detect relations. So argument detection, what are the arguments between which you want to extract these relations. Then there is a domain and range filtering, then the feature extraction for the relation, and some machine learning classifier that extracts these relations. That this can be done either per relation or per pattern approaches. And towards the end, there is another module, conflict resolution, that decides in case there are still two remaining relations that compete, then this module decides which one should be considered between the pair of arguments. Now, there is another module that is very useful, and this is so-called semantic calculus. This is something that is very dear to me because I've been invested about 4 or 5 years in my time in doing this kind of work. It's to combine semantic relations to extract new semantics from that. So the idea is that if we have already relations R1 extracted in R2, you want to combine, see if there is a reason to combine these relations to end up to conclude another relation, R3, which has not been detected by the parser. So here's an example. In this little sentence, John went to the shop to buy flowers. This relation with the black down here, I extracted by the parser. So John is the agent of going, and going has location to the shop, and the purpose of going is to buy, and the theme of buying is flower, was being bought. So these kind of relations can be normally extracted by a parser, but yet there are other relations that could be derived from these relations by combining the two. For example, John went to the shop. We know that going is to the shop, but John is on the location shop, and that is also by combining agent with location. And the shop has also so John has the intention of buying. You combine purpose here with agent, and sometimes that gives us an intention. So he had the intention to buy flowers, and there's a possible possession relation. The shop was open, then there is a possession of the flowers were in possession of John. So that brings a very interesting idea. Some of these relations that are extracted speculatively are, you can link some probabilities. If the shop was open, then he got the flowers. But if the shop was closed, then maybe he didn't get the flowers, right? So that's what we mean by semantic calculus. To combine these relations to derive new relation and to put some probabilities in top of this relation that we extract. So here are more examples about a semantic calculus. We use the property of transitivity of ISA relation. ISA, X is Y and Y is Z, then X is Z. Agent and cause relation, theme and location, is location, so on. I just want to allude to some usefulness of this semantic calculus in case you want to find out a new relation that was not generated by the semantic parser. Let's say you want to know if two people are associated together, right? What this axiom is telling us is that X is an agent of Y, and Y is writing. So John writes a letter to Bob. Okay. Then John is the agent of writing, and what's being written is a letter, and the recipient of that letter is Bob, right? So we can represent that in logic, and if Z is a communication, it's a letter or an email, we can conclude that John has communicated with Bob. And more than that, we can conclude that John is associated with Bob in some form, right? You want to know new relations, and I'm saying that these new relations can be arrived at by using some OR relation that we already established and putting some constraints on the arguments of the relations. And this certainly is an alternative to implementing, to rebuilding the semantic parser, which require a lot of training and it's very time consuming. It's much easier to write this kind of axioms if you're interested in some domain. So now let's go to some events, because that was one of the important steps in a hierarchical organization. Events along with entities provide understanding of the world by relating actors to the actions and states, and events basically are responding to what happened. So events can be verbs or nouns. You have to be very careful because you don't want all the legal all the verbs to be understood as events. If you're not careful, you end up with too many events. So you have to filter to get to the important events. Okay. So the way we represent events is that, say kidnapping is an event. An event certainly has a time and location. That we know that. They have to have a time and location. They may also have a duration. An earthquake lasts maybe minutes, the most. Kidnapping is an event that took place, and then there are consequences. So then also you want to know if there are instruments that have been used in the events, who are the participants of the events. So all of these are slots that are part of the event structure. That's how we implement events. Very complex structures, and some of these structures may be filled in by the text information, or they may not have any fillers. So once you represent events and you fill in the slots, then you can perform event relations like causation or temporal relation, fire has occurred before the kidnapping, and you can do some reasoning about events. Okay. All right, so these are some properties of the event. First we have to detect the events, the properties of the events, and event-event relations. Now, co-reference of the events is very important step, because if you have many documents, and let's say they talk about some kidnapping, in one document they refer to that event in one way, in another document in another way, and you want to know if it's the same event. How do you know if it's the same event? Well, the time has to be the same, and the location has to be the same, and the participants will have to be the same. So you check in the slots, the field of the slot, and then you figure out that, yes, it's a correct. Now, there are other methods to do event reference, like LDA, the British structures. So there are these semi-eval competitions that take place organized here in Europe, and if you participate in them, like we did in 2007, some software was developed about event relations. I said the co-reference is important. The fact that this kidnapping is the same as kidnapping over there. This kidnapper is the agent of kidnapping this event. The Dea Flores refers to he, right? So you have to co-refer in order for the text to be coherent, consistent. Okay. Now we want to see if we can have a model to represent the implicatures as well. That could be merged to this hierarchical organization of knowledge. So here's the model that we came up with to how to represent implicatures. So you have the speaker, and here the speaker has some utterances like what the speaker has said, but also what the intentions of the speakers were without being uttered. So it's a set of small u1, um. These are the utterances and the intentions of the speaker as well. Right? So let's represent mathematically that. But here, on the other hand, we have the explicit text meaning, TM, plus what's being implicit, derived via inferences, and what's being implicated. So all these symbolically, the sum of these things is what the hearer should understand. Okay? Now, in addition, there is a context, and there is also some common knowledge, and then Gratian knowledge. So if you put all this together, you end up with a model like this: the speaker's intentions, the speaker utterances, and here is the explicit meaning of text, HTM, the inferences that are extracted, and here are the implicatures that the hearer understands. And if this coincides with the intentions of the speaker, then we've done a good job capturing this SOI. Now, in the middle, there is common sense knowledge and ontological knowledge that is useful to get this explicit, implicit, and implicated meaning, but then Grice Maxim information and context only play a role in deriving the implicatures. So can we have some functions, how to compute these elements? That's the purpose of this project, especially for tweeters. So here's what we did. We use a logic prover that we have developed some years ago. So that statement put out by A in that example with the prompt, with the dinner, is transformed into logic. Now, I'm not going to go over this, but this is logic form that can be derived automatically from that sentence via, like I said, a syntactic parser. And this is what's being understood by the hearer. This is the output of the machine. It understands it's a dish, that it's part of a meal, and is a relation, that this is a meal, and so on. And this is what's being, these are the implicatures that shows the user's strong feeling. There is excitement that A had, and some other semantic relation here. The context has been 0 because there is no context yet. Only A has uttered this, and B didn't have a chance to respond. But then if you go on, okay, well, so this is the block diagram of the system, and then I'll show you some snapshots. So the input, the text, goes into this logic form transformer, and that is presented to a logic prover that's called Cogex. There is, by the way, a paper about that. If you look at Calling 2003, there is a paper describing the logic prover that receives logic forms as the input and does some reasoning. And this prover also receives all kinds of knowledge that's necessary for the proof to be done. For example, the lexical chains, semantic calculus, common sense axioms, and Grice maxims in logic form have to be input to this prover. The prover proves by refutation, has a hypothesis that needs to be proven, and then it reverses, negates the hypothesis, and if the proof leads to nil, then the hypothesis is true. Proof by refutation or opposite. And so we derive these aspects, what's being uttered, the here, explicit, implicit, and implicated. And that is sent back, and it becomes a context. As the conversation goes, what's being said becomes part of the context, and the new sentences will be treated within that context, which was empty in the beginning, or unless there is some context about the reason that you want to start with. So at the end, you get the implicatures. So we implemented a system like that, and what we did, we transformed the Grice's maxims into logic. We look at some tweets, something like 200 pairs of conversation from the web in two languages, in English and Arabic. And we help the system by providing the common sense axioms that are relevant to that conversation. Because that's one of the bottlenecks that you run into when you try to implement something as complex like this. All of a sudden, you don't have an axiom that will allow you to make the proof. So we have manually provided these axioms that were used by the prover. And semantic calculus axioms, we already have them. Race per chance can be derived on the fly. I'm not sure if you know what I mean by expert chains. Given two concepts, the system can extract a chain of concepts that shows the semantic connectivity between these two concepts. Right? It's very useful tool. We use that in question answering, in textual entailment, and you always need to establish, for example, that like beating somebody is the same thing as knocking down in boxing, right? So if you say John beat Bob, he knocked down Bob, it's the same thing, right? So how to establish that is a semantic coincidence between beating and knocking down. All right, so this is the system, and like I said, this was implemented at Limba in 2 languages, this is the input. It's small, but it's the example that I mentioned, and it's just a snapshot of the system output, just to convince you that this has been done and was working. Okay, so a little bit more about projects. It's approved by reputation, and projects was built on top of a publicly available logic prover, Prover 9 or Alta. Maybe some of you have heard about that. It's available, it's publicly available, and you can modify that, and you can build your own prover from that. That's what we did. So our innovations here in projects was to send to projects some text that was transferred into logic, and that logic prover after Prover 9 does not have that part. So you have to have that part to be useful. So basically this project has a set of support, like any prover would have. It's a list of clauses that describe the problem on the study, and there is a usable list that contains the axioms that are needed for inferences. And while there is something on the SOS, the set of support, the prover tries to find proof for those statements, and then there is a way for the prover to stop when SOS is empty or the run out of axioms. Well, okay, so I'm kind of running out of time. I just want to say that to implement a complex system like that, you need to transform all kinds of knowledge into axiom, into logic. And the expert chain, then you have to have this semantic calculus axioms, or you might not have, you might have something else, but something that will give you a lot of information. And word knowledge axiom, for example, people are usually the agents of their communications. If a person is expressing approval of a person that is the agent of the action, then you express approval of an action, of the action. Things like that are common sense, that are very difficult to put your hands on, but then you have to write this by hand. That's what we did. And all right, and the Rice maxims were transformed into logic. Like, for example, the relevance would be there must be at least one common predicate between the logic forms of the speaker and the context, unless otherwise it's not relevant. So things like that. So let me just conclude with some thoughts. So one thought is that it's possible to implement a complex software system that extracts knowledge from text and even implicatures, provided that you put the right input into the system. There is need for word knowledge. There is need for common sense knowledge. There is a difference between word knowledge and common sense. Word knowledge is, Russia is the largest country on earth, right? China has the largest population, right? This is word knowledge. Common sense knowledge is if you have a round object on an incline, that is going to roll down. Or if I drop this pen, then gravity is going to take it to the floor, right? This is like common sense knowledge. It's common sense because everybody knows it, and it's very difficult to acquire this knowledge. There is need to handle context and the relations between the participants and knowledge that is shared by participants. So a lot of work to be done, and it's very exciting to play with literatures. Let me reserve a few minutes for questions. So I'm done.
Thank you very much. We have about 8 minutes for discussion questions, please.
So you have mentioned in the introduction examples that the system can generate ambiguous implicatures, like an example of the penis and the girlfriend.
Right.
So, but in your Twitter project, you use the implicatures as a context for the next.
For the next round of conversation,
yeah. So
yes.
how do you handle the ambiguous implicatures? Do you keep them both?
Yes. You keep them both. It grows like a snowball. All kinds of things can be extracted from text, and then you do not know until maybe later on that that is the right or wrong implicature. So you keep them in a stock, and then the context will tell you which one is valid and which one is not. Sometimes there is a competing, so you have to put some numbers, figure of merit, which one is to be believed now. And see, this is a process that is non-monotonic, as opposed to other derivations that are purely monotonic, more and more information. Here, you can extract some information that will invalidate some of the information extracted. That's perfectly normal in conversation, right? We believe something now, and then later on we change our mind about it. So same thing with machine.
And you mentioned that you can apply the probabilities for this ambiguation.
Right. You have. Sorry.
Have you implemented this in this?
No, we did not implement probability. It's just a phone. Yes.
In your example, isn't it strange that the people who who were hired were not the kidnappers at the moment they were hired? Fired.
Fired being laid off.
Hired.
Right.
Yes, hired.
They were upset. They were upset, so that's why they went and kidnapped the guy who fired.
So isn't it strange that they are called kidnappers at the moment when they were not kidnappers yet?
See, but the text was written by a newspaper person later on, so it was after the fact. So the kidnapping had occurred. By that time it was written. So yeah.
So those that were fired, they were not kidnappers. They were prospective.
So what was going on there is that somebody, Gilda Flores, lay off people, fired them, said, go on, don't work here anymore. So, and then they were upset, right? So they went and kidnapped Gilda Flores.
What is the mechanism to know at which point in the text you have to use, for example, a quantity maximum?
So eventually, all those maxims are transformed into this logic, and it's just another logical form. Yeah, just logical form. The quantity maximum. So, well, we have to look at the specific. It doesn't come to mind, but it's just like any other maxim. It becomes a logic active form that's being used in the proof. Right.
But how do you know that you have to take this maximum?
It's part of the stock. So the logic prover, probably I was not clear. The logic prover uses Gauss maxims, uses lexical chains. All those things are part of the what's true in the machine, and it uses whatever axiom is related to the hypothesis that you want to prove. So if the machine calls the axiom automatically, you don't know if it's a quantity maximum or quality maximum at that time, because it's part of the stock of logic in the machine.
If I understood correctly, you can deal with the implicatures or implicated meanings by first relying on the general knowledge, or what we call pragmatics, common sense, background knowledge, the cultural models. And the other, yes,
another aspect.
there is one. Yes. And therein too, the context. So the ongoing meanings created in the process of this communication. This communication.
Or the context could be something that you and I know from yesterday, from half a year ago. If I meet you a year from now, you have a context, right?
Okay, but and then there may be a conflict between these two variants in calculating the implication, right?
Right, could be.
Wouldn't be it always, and I mean it's always as important, wouldn't it be always safer to rely on the second part of meaning, the context? Because context is something that is between you and me, either here and now or maybe sometime. And common sense, general knowledge, well, I presume that you have the same idea of what, I don't know, justice and love is, but it's just presuming, and I cannot be sure about it.
Well, it's a good question, and we did not experiment thoroughly with this. Like I said, the system was just built just to prove that the contract. We just built a system to prove that it's possible to extract implicatures. That was hard enough. So we did not experiment with different kinds of context and so on. But also the context may change, so we have to put the timestamp on the context, right? And then social cultural aspects. So I cannot answer your question exactly.
Is there any straightforward difference between the notion of common sense knowledge and word knowledge?
Yeah. Well, that's very easy. Word knowledge is found in books, is found in encyclopedia, and you know, right. Common sense knowledge is typically not found there because it's so simple, we're so used to it that you know, like a child will know that will not touch a fire because it burns, right? It learns from early ages. That's not word knowledge. That's common sense knowledge.
Why should it be in some encyclopedia file?
No, it's not. Common sense is not. But word knowledge is. The information about Russia being the largest country and people the surface and everything, that's word knowledge. It's not common sense. Right?
It's common sense.
Well, it's common sense. I know that the boundaries is, you know.
And the information.
But you know what I mean, right?
Information about the fire can be in some dictionaries. I mean, it's hard to draw this line between common sense and
I tried to do some work to extract common sense, and it's very difficult because it's not stated. The fact that in America the president is living in a White House is so common knowledge that hardly you have a statement saying that he lives in a White House or something like that. So
It's common sense.
it's common sense, yeah. You know, 5 years. I mean,
Where else would you live?
All right.
There is time for one more question, please.
Would happen if there are two sentences which contradict each other?
That's well. For example, when people argue, right? You can have, right? There could be contradictions for many reasons. The system will be lost. Will not know what to do. So then, you know, that's not something that we're trying to achieve here. We're trying to do the easy thing, just extract some figures that more or less obvious. One last question by my friend Carol.
Back there.
The
dark part of the room.
It was just related to the question before last. So have you looked at naive physics? So one knows that if one drops a ball, it will hit the ground.
Right.
That's a sort of common sense knowledge, but it requires knowledge about how the world works. And
Like I said,
people have worked on this. So
we try to help the system. Yes, it's true. But yet, still, from somebody who was trying to implement the system, that was one of the biggest bottlenecks. The lack of word knowledge and the common sense knowledge that to be massively available so we can put into the system. That's the biggest problem that I see to automating some of these things. So yes, that knowledge is in different books, but how to get to that knowledge with an action.
Well, thank you very much for a very rich